Just days after the end of URC 2018, the Mars rover design team at Missouri S&T began the design process for our next rover. New requirements were developed based on lessons learned in 2018. After 9 months of designing, manufacturing, and testing, we are proud to introduce our 7th rover, Valkyrie.
Our team structure is comprised of 8 project-based subteams. Each subteam is interdisciplinary, which improves communication between our 150 members and allows greater knowledge transfer across the 18 majors we represent. Our testing schedule this year is more aggressive than ever. As such, the team has constructed an indoor testing facility, which allows for around-the-clock testing in all weather conditions. Additional testing will be conducted outside, allowing for both full task simulations and comprehensive system development.
The mechanical core of the rover comprises of a unique multi-link suspension optimized for rocky terrain, an auxiliary mounting system, and a lightweight electronics frame. The drivetrain uses carbon composite and aluminum linkages, a modular aluminum chassis, and custom nitrogen gas springs to create 7 degrees of freedom for exceptional articulation over rough terrain. Teleoperation is facilitated through the use of a 2-axis stabilized camera gimbal to improve field reliability. Improved design calculations resulted in a 20% increase in range of motion and allowed further structural optimization. These new features were developed and tested using CAD and finite element analysis and fabricated through the use of advanced manufacturing techniques.
The rover is powered off a custom 8S9P 18650 lithium-ion battery pack. At 33 volts and 32 amp hours, this pack is capable of supplying power to all rover systems for over an hour of continuous operation. This system is complete with a battery management system to monitor the pack's current draw, cell voltage, and temperature throughout the task, and protect it from critical failures. Power is sent into a custom distribution and control board which utilizes 2 switchable 12-volt 20-amp buck converters and 7 managed pack voltage outputs, enabling individual current monitoring and control of power sent to on-rover communication systems, microcontrollers, actuation devices, and our 3 brushless motor controllers, capable of supplying up to 30 amps to each of our 6 main drive motors. The robotic arm utilizes 2 custom brush DC motor controllers, allowing for independent closed-loop PID position and velocity control of up to 8 joint axes.
The robotic arm is a 6 degree of freedom dual end effector actuation system that utilizes 3 sets of 3D printed differential gears and brush DC motors to drive the arm into any position within its working envelope. Utilizing and improving upon the inverse kinematic control developed last year, the team will be able to perform the extreme retrieval and equipment servicing tasks with controls that are aligned to the camera's perspective. The arm is composed of aluminum carbon composites that provide the large strength-to-weight ratio of carbon with the ability to locate parts together with machined aluminum. The use of carbon and the simplification of mechanical systems through differential gears has eliminated 4 kilograms. This, and the conversion to belt-driven systems, helps to improve the response of the arm's motion by reducing the inertial torque and the backlash between the driving and driven components.
This year, we restructured our legacy code into a state machine to improve its readability. Valkyrie's navigation board implements a magic filter to generate an accurate pitch, roll, and heading by interpreting data from a 3-axis IMU. To improve Valkyrie's performance in the autonomy task, our team will employ a spiral search pattern to methodically search for waypoints beyond the given coordinates. When Valkyrie spots a tennis ball, its state machine exits the search pattern and begins tracking the waypoint with a color and shape mask. Simultaneously, TriCam, our custom 3-headed collinear stereoscopic camera, and a 1D LiDAR system work in tandem to detect potentially hazardous obstacles. TriCam generates a dense 3D point cloud, allowing Valkyrie to better visualize its environment. In order to handle data more effectively, we have upgraded to a Jetson TX2 for its parallel processing capabilities, allowing us to complete the autonomy task.
This year, the science team has elected to complete the science task by utilizing a diffraction grating-based custom UV Raman spectrometer powered by a deuterium lamp and supplemented by onboard sensors. The spectrometer is mounted externally on a system providing 3 axes of motion to allow analysis for the samples in situ. Ibuprofen calibrates the spectrometer to detect varying concentrations in samples, and a database of chemical compounds automatically compares spectral data to known compounds during the task. Spectral analysis along with visual fluorescence is used to search for biological compounds in minerals, such as porphyrins, hopanoids, and calcite, whose presence indicate life. A large diversity of organic compounds indicate extant life, while limited presence indicate extinct life. Absence of these compounds conclude that life does not exist at the site.